Hi, I'm trying to study for a chemistry test, and I can't really stay focused. And filming myself, or like if you can't focus, filming yourself helps because it keeps you accountable. So I figure, okay, why not? And studying can make some fun sounds, like typing and clicking and whatever. I don't know. So that's what we're gonna do. I'm gonna study and yap, because also a great way to learn is to explain. So I'm gonna go through the study guide, and if I don't know an answer, I'm going to Google it or use Control F and find the keywords in the textbook and just talk through them until I figure it out. I think that that's a great game plan. Hello? One of my sections is marked that I didn't complete all the items, but I definitely did. Lies. Yeah, okay, I'm trying to find the study guide right now. Was it right there? It's because I didn't view the practice questions. No, it thinks I'm good. Right. Okay. Study guide. So, the unit we're doing in chemistry right now is acid-base reactions. And full disclosure, I definitely rushed through the readings and the assignments, right? Because they were assigned right before spring break. And I was just ready to get on spring break. So now I'm paying the price because I don't really remember what the content was. My friend brought me this Dr. Pepper, and then he dropped it. So it's kind of smushed, but Dr. Pepper is Dr. Pepper. I feel like it's going to be really loud. That didn't work at all. Well, innovation. That's brutal to try to drink it that way. Hold on, actually. Move my water bottle. Got this collapsible straw. It's Coca-Cola. Don't tell Coca-Cola. Got this collapsible straw. I got it in like the first week of my first semester at like a welcome week activity. And I was like, oh, well, that could be potentially very useful. hasn't been yet, but I think it is. Oh, that's a fantastic sound. I don't know if it'll do it again. Oh, I hope that was heard the first time around. Seems fine. Seems that. That's pretty good. It works fine. Where do I put this? Okay, put it in here. Oh my gosh. Get to the point. Okay. The big ideas for this unit are: chemical reactions involve rearrangements of atoms to produce new chemical species with new bonds. Chemical reactions produce new species with properties that cannot be predicted. Emergent properties. Chemical reactions involve only changes in arrangements of atomic cores and valence electrons. Chemical reactions can be classified by how the valence electrons behave during the course of the reaction. For example, acid-base reactions or redox reactions. Energy changes in reactions arise from the changes in bond energies as bonds in reactants are broken, which requires an energy input, and new bonds are formed, which releases energy to the surroundings. There was so much about acids and bases. Like, the whole thing was acids and bases and pH. pH isn't even mentioned. I guess. What's the point of pH then? Goodness gracious. Sometimes I wish that nobody ever discovered electrons. Like, when I was in calculus, I was very angry at Isaac Newton for discovering calculus. He's the one that did that, right? Hold on. Yeah, Isaac Newton. Calculus was primarily introduced by two scientists, Isaac Newton and Gottfried Wilhelm Leibniz. Okay. The Newton-Leibniz calculus controversy. Oh, I don't know who it really was. Interesting. Well, I was upset at both of them, because I did not want to be learning that. Okay. Key skills. Number 1. Explain, using a molecular level explanation, the difference between a chemical change and a phase change. Describe the evidence you would use to support your explanation. Okay. Well, on the molecular level, the difference between a chemical change and a phase change. A phase change is the same molecule switching phases. So, like water, it's ice, and then it's water, and then it's a gas. And then it goes from solid to liquid to gas. Very, like, what am I trying to say? It goes from solid to liquid to gas without changing the actual structure of the H2O molecule. But in a chemical change, it'd be like the reaction between hydrochloric acid and what is it called now? Sodium hydroxide, where they react and like the actual structure of the molecules changes. It makes hydrogen, it makes water, and chlorine and sodium, which form ionic bonds become NaCl. So that's like changes. That's what I'm gonna go with. Number 2. Identify the molecular structural features that lead to acidic and basic properties in a molecule. Explain why these features are important. The molecular structural features that lead to acidic and basic properties in a molecule, okay? The molecular features that lead to acidic properties is typically, well, it depends on the model. In an Arrhenius acid-base model, well, it's protons, okay? So like acidic molecules are typically positively charged. They have a hydrogen that can donate. Or donate protons, like a positive charge. So they're usually, so they've got extra protons. Bases have extra electrons or a negative charge, and they want to accept more protons. Okay, and here's the thing. The definition changes slightly depending on which model of acid bases that you're thinking about. So on the Lewis acid base, the acid is an electron pair acceptor. So the acid must have a place to accept an electron pair, or like electrons. So they're species with empty or partially empty orbitals of available energy. So, positively charged because there are electrons missing they would usually have, and they're willing to get those electrons back. And bases are electron pair donors, which must have lone pairs to donate into the bond, which is why negatively charged molecules are typically bases, because they have extra electrons that they are willing to give up to reach stability. Okay, I get it now. Great. Number 3. No common strong acids, HCl, HBr, HI, HNO3, H2SO4, and bases, group 1 or 2 metals with a hydroxide ion, such as NaOH and KOH. I know that. I know those. Well, let me see if they're all on my note card. HCl, HBr, HI, HNO3, H2SO4, NaOH, KOH, any group 1 or 2 hydroxide. Yep. I got that down. What is group 1 and 2? My periodic table sheet. So group 1 is hydrogen, lithium, sodium, potassium, rubidium, whatever CS is, and francium. Group 2 is beryllium, magnesium, calcium. I don't know what SR is. Is BA barium? Is RA radium? Wait, this is embarrassing. Hydrogen, lithium, sodium, potassium, rubidium, caesium, CAESIUM, and francium. Okay, so I was basically right on the first one. Beryllium, magnesium, calcium, strontium, barium, yes, and radium. I ate that up, okay. I knew all of them except for one on each of the rows. I think that's good enough. That's not what I'm being tested on. Okay. use the words strong, weak, dilute, and concentrated appropriately. Okay, well, a strong acid dissociates completely in water. A weak acid does not. A dilute solution has a low concentration of an acid, strong or weak. It doesn't say anything about the acid strength or the base strength. This goes for bases too. Strong bases dissociate completely, weak bases do not. And concentrated means that there is a high amount of acid or base in the solution. It's leaking. Wait, should I? Wait. What if? Oh no. Does this fit? I don't think it does. Fine. The straw is like so bent that it's leaking. Not sure if I have a napkin or something. Oh wait, I do. College tip. Just bring a roll of toilet paper from home. It's like mini paper towels, mini napkins. Easier to store. Great. Okay. Predict and explain relative strengths of a range of related acids or bases using thermodynamic or electronegativity arguments. Okay, what was this? I remember this. Pretty sure. Okay, so this is obviously talking about entropy and enthalpy. So here, let me try to do it without looking at my notes. Oh wow, look at all these pages. Chemistry is a lot. Gosh, I'm itchy. My nose is itchy. It's getting back to be allergy season. Okay. So, enthalpy. Enthalpy is determined by the strength of the bonds. So if the bond between, let's just use acids, if the bond between the atoms in an acid that are breaking are very strong, it's going to take a bunch of energy to break those bonds. And then the energy that is formed or released by the forming of OH bonds in the water that is being diluted in will not be strong enough, will not have, it won't release enough energy to balance out what it took to break those bonds. And electronegativity comes into play because electronegativity increases across a row and decreases down a group. So the most electronegative element, here's my periodic table, is fluorine. You don't count the noble gases because they're not really reactive, so they don't really draw energy to themselves because they're very stable. But fluorine is most electronegative element because it has more protons, so it draws its electrons in closer, and it's small, so it draws its electrons in closer, like more tightly, because the electrons are closer to the nucleus. So the bonds between, like, an HF is a relatively weak acid, I believe, because yeah, HF is a relatively weak acid because the bonds between hydrogen and fluorine are so strong that it's difficult to break those bonds, so it doesn't dissociate into its ions completely in water. And that means that it's weak. I'm just rambling. It makes sense in my head. I get this. I can do this. Okay, number 6. Explain how the progression of Arrhenius, it's Arrhenius, so I don't know if it's Arrhenius, Arrhenius. Arrhenius. Okay. Arrhenius. Arrhenius. As a base. I lost my tab. Okay. Does anyone else have like 50 tabs open all the time? That's me. I'm a tabs girl. Explain how the progression of Arrhenius, Bronsted-Lowry, and Lewis acid-base theories build on each other. The Arrhenius theory was just protons moving back and forth. And it had to be in water. The Bronsted-Lowry idea included hydrogens. Something was added. It's not just protons, I don't think. Oh, it is protons. Oh, okay. I was wrong. Bronsted-Lowry is proton donor, proton acceptor. Arrhenius is the acid or base dissolving in water, where acids dissolve and give H plus ions, and bases dissolve to give hydroxide. So acid dissolves into protons, base dissolves to give hydroxide, and that's it. And then the two things react to form a salt and a base, like the reaction between HCl and NaOH, hydrochloric acid and sodium hydroxide. The sodium hydroxide is the base. It dissolves in water to produce a sodium and a hydroxide. The hydrogen chloride dissolves and produces a chlorine and a hydrogen, which is a proton. So the hydrochloric acid is the acid, and the sodium hydroxide is the base, and then they form NaCl, which is a salt. So salt and base. What? Oh, water. Water's the base. Okay. Bronsted-Lowry is acid is a proton donor and base is a proton acceptor. So it's talking about like hydrogens go back and forth and are donated and accepted. So an example of that is NH3 plus H2O, making NH4 plus and OH minus. So proton leaves the water, which acts as the acid, joins the base, which is the ammonia, to make ammonium and hydroxide. Okay, yes. Lewis acids and bases, those are the electron pairs. So Lewis acids accept electron pairs and Lewis bases donate electron pairs. So it starts with just dissolving in water and like adding protons and OH, then it's proton donation, then it's electron pair donation. Great. Number 7, predict the products of acid-base reactions based on the relative strengths of the acids and bases. I think I can do that. Right. that. No, that was probably so loud. The cut is because I just got a text and it was really loud. Okay, so predict the products of acid-base reactions based on the relative strengths of acid. I assume that means like, yeah, I think I can do that because it's like HF would have HF molecules and H3O plus and OH and F and yeah, and F. HI, which is this very strong acid, would have H3O plus and OH in there, and well, maybe not OH is necessary to put in there, but it would like plus H2O would make OH and H3O plus because those are always there, and then it'll only have H and I because it dissociates completely. Yeah. Predict the extent of acid-base reactions based on relative acid base strength. Oh, I just did that. Like how far it's going to break down. Okay, number 9. Use curved arrow notation to predict the products of Lewis acid-base reaction and simple nucleophilic attacks at electrophilic carbons. Attacks. Oh my gosh, that's so funny. I can do that. That's just a skill. It's right here. I do that. Yes. Okay. Calculate pH from given concentration of strong acids or bases. I can do that. Can I practice problems? Okay, I think we're moving on to module 7.2. pH. Yeah. Okay. pH equals the negative logarithm of the concentration of hydronium. And the concentration of hydronium is 10 to the power of the negative pH value. Okay, I know this. Use pH to calculate the hydronium or hydroxide. I can do that. pH, okay, so the concentration of hydronium is 10 to the negative value of the pH, and then the concentration of OH is the negative 10 to the negative value of the OH, and since the concentration, what is the relationship between that again? Oh yeah. 14 minus pH is POH, because they must always add up to 14. Because the concentration of OH and H in water is 10 to the negative times is some, what is it? Is it 1? Something times 10 to the negative 14. I think it's just 1. Oh yeah, 1 times 10 to the negative 7th for each of them. So it's 1 times 10 to the negative 14th is the concentration of both of them. Which is why the KW, what is that constant again? What is that called? The ionized, okay, the concentration constant. The ionized H2O concentration constant is 1 times 10 to the negative 14th. Okay, I can do that. Use pH of solutions of the same concentration to determine relative strengths of acids and bases. Okay, I can do that because the higher the pH, or the lower the pH, the more acidic, the higher, the more acidic it gets. So, the strength of acid, okay, a base is going to have a very high pH. So a higher pH is a stronger base. Yeah, I can do that. That's just logic. It's been half an hour. Oh my god. 13. Identify and explain why acid-base reactions are different from redox reactions. acid-base reactions are different from redox reactions because redox reactions involve the change of oxidation numbers, which aren't real, but they're important. What's the actual definition? The difference between acid-base and redox reactions. Acid-base reactions are triggered by attractive forces. So like the proton being attracted to the negative charge on the base, and revolve around proton transfer or lone pair transfer. So they're just transferring protons, they're transferring charges, and it's by attractive forces. Redox reactions are triggered by differences in electronegativity and revolve around the change in electron density. And they can occur between two polar substances. Okay, so triggered by differences in electronegativity. Yes, I did know that. Okay. 14. Recognize redox reactions by looking for changes in oxidation numbers. I can do that. What are the rules? Let me just find those. Okay. The charge of ions is their oxidation number. Covalently bonded elements are imagined to have all electrons transferred to the more electronegative atom. For example, the oxidation numbers in H2O, hydrogen is +1, oxygen is -2, because both of the imagined electrons from the bond are on the oxygen. Oxygen is always have an oxidation number of -2, even if it has multiple bonds with an atom that has more than one electron. I'm not sure why, that might trip me up. I couldn't really find a definite answer on whether or not that's actually true, so don't quote me on that, but I don't know. It says O is always -2, the big old question mark. Maybe I should have gone office hours, but it's a little late for that. Okay. Elements always have an oxidation number of 0. All bonds are the same, they're pure, and there's no polarity. So like H2 has, both of the hydrogens have an oxidation number of 0 because there's no polarity in there. There's no change in electronegativity. Okay. Spot redox reactions, redox reactions, see if oxidation number changes from reactants to products. A handy little acronym is called OIL-RIG. Oxidation is loss, reduction is gain. So oxidation is loss of electrons. So being oxidized is losing electrons and becoming positively charged. And reduction is a gain of electrons, and that's confusing, but if you think about it as like the charge of the molecule, the molecule is getting reduced when it gains electrons because the charge is becoming more negative because it's gaining electrons. And oxidation, I think that I read that it's from the fact that the first examples of redox reactions were combustion reactions, and the oxygen transferring was important, something like that. I don't know exactly why it's called oxidation, but okay. 15. Use bond energies to predict and calculate enthalpy changes in reactions. Okay, we talked about this. I talked about this. So the bond energies, right, you get like a table of bond energies, and you can add up the bond energies of the products and subtract the bond energies of the reactants, because the reactants are breaking the bonds. Okay, wait. No, it's the bonds formed on the product side. The bond energies of the bonds formed on the product side minus the bond energies of the bonds broken on the reactants side. So that way you get the energy when that's released by the whole reaction, because the bonds broken on the reactant side take in energy, and the bonds formed on the product side releases energy. So the enthalpy change can be estimated by the relative bond energies. Except the bond energies are like that you get in tables are just estimates because they're all taken in the gas phase at perfect standard conditions, which is like hardly ever true. So they're just estimates to figure out whether or not they're going to be super exothermic or endothermic or whatnot. Okay. 16. Construct drawings and graphs to show how energy changes over the course of a reaction can be determined by the bonds that break and form. Ooh, I knew this one. No. It's the one. I'll find it. Where you use the graph in the drawing, you put the lines and you say reactants and then energy. Like, I'll draw one. So okay. Wait. Okay. So if this is the energy. Oh. Is it over time? Yeah. Sure. Don't mind the handwriting. So, you can see the whole reflection. So if these are the reactants down here, this is just where they are. I don't know exactly what that means, but so the reactants are down there. And then this here, this is an example of an exothermic reaction. So the reactants are down here, and this space is the energy that it takes to break the bonds in the reactants. So a bunch of energy goes into the system. The energy spikes. The free ions are up here. That's what this says. Like, this doesn't actually happen in real reactions, which is why this is an estimate. The reactants. Oh, that's not what I meant. The reactants. Ooh, I'll use the laser pointer feature. So the reactants down here, they take in a bunch of energy, and then up here, this is as if every bond in the reactants that needed to break broke, and all the pieces are just separate and floating around, which doesn't actually happen. Like, a bunch of things happen simultaneously, whatever. That's why it's an estimate. And then this space, that's a really, you know what, I'm just gonna use the shape tool because it's better. Then this space is the energy released by the system. So this is like, these three are all the system. So this space right here is the energy that is released when the bonds form again in their new places. So for example, if the reactants are HCl and NaOH, this would be if HCl, Na, and OH were all just floating around after breaking all their bonds. And then the products area down here would be the amount of energy that is left in the system when they switch to being H2O and NaCl. So in this example, since the reactants are here and the products are down here, this is an exothermic reaction because more energy was released than was pulled in by the system to break the bonds. So that's how you identify an exothermic. But if the products moved up here, what would happen then is, oh my goodness, is this would now be the space that indicates the energy released by the system when bonds break. And since the products are up here and the reactants are all the way down here, this is now an endothermic reaction because more energy went into the system to break the bonds, so more energy was pulled out of the surroundings, which makes the surroundings colder, than was released by the breaking of the bonds. So these don't balance out. So overall in this reaction, more energy went into the system and out of the surroundings when bonds were being broken than came out of the system when bonds were being formed, which is why the surroundings end up colder and it's exothermic. Endothermic. Surroundings end up colder and they're endothermic. If more energy is released, like if this goes back down here, if more energy is released, then it is exothermic because this value is greater than this value, which releases energy to the surroundings, which makes the area warmer. Well, that was helpful. I've actually never understood it in that much depth, so that's great. Okay, number 17, this is the last key skill. Use molarity to calculate amounts of reactants and products for reactions in solution. Oh. I don't remember how to do it exactly. I'm pretty sure it's just conversions, just conversion factors. So I will refresh that when I do the practice questions. I'm pretty sure it's just like, okay, you use like the moles, because moles over liter, and then you do the amount of liters or milliliters that are in the solution to get liters canceled out. You convert milliliters to liters. To get liters canceled out, and then then you're left with moles, which is the amount of moles. Oh, and then if it's amounts in mass, you use the molar mass, the molar weight of whatever the reactant or product is, to cancel out moles and then get grams. But if you're going from the molarity of one thing to another thing, you can use the mole ratios in the balanced chemical equation. Like if you need 2 moles of something to produce 3 moles or something, or like whatever, you can use those numbers to convert. Okay, no, I know how to do this. Let's practice it later. Okay. Well, learning objectives and key skills usually overlap, so I want to just go through these super quick. Define Arrhenius acid and bases. Anything that, so what was it? Arrhenius acids and bases. Arrhenius acid dissolves to produce protons. Arrhenius bases dissolve to produce hydroxide. Define and recognize a neutralization reaction. The heck is a neutralization reaction? Oh wait, that's a neutralization reaction is when a base and an acid reacts to form salt and water. Oh my gosh, wait, that means my notes are wrong. Hold on, I've got to fix that. Because I said earlier, I just read it off. React to form a salt and a base. No, that's not right. And water is neutralization reaction. RXN is the abbreviation to reaction. Yes. Neutralization is a salt and water, an acid and base reacting to produce a salt and water. Great. Define and identify common strong acids: HCl, HBr, HI, HNO3, H2SO4, and bases NaOH and KOH. Okay, I can do that. Define and identify weak acids and bases. Anything that's not those. Anything that doesn't dissolve. I have to cough. Okay. Okay. Define and identify weak acids and bases, compare and contrast weak. Anything that doesn't dissolve all the way. Like NH3 and which is ammonia, and HF. Compare and contrast weak and strong acids and bases. Okay, that's the electronegativity thing, and like dissociating completely, which I can do. Define Kw and the autoionization of water. Kw, what was that? The concentration constant? Yes, the concentration constant of water. K sub W. The autoionization of water is the idea that hydroxide and hydronium, which hydronium is just another word for the hydrogen, but hydrogen is a small and very charged ion, like H plus is a small and pretty charged ion. So in water, it would be surrounded by the oxygens on the water or whatnot. Like it'll have what's it even called? A shell around molecules. So it really just joins onto one of the lone pairs of water, so it's just better represented as hydronium. So the autoionization of water is that hydrogens are always jumping, like they're always converting to H2O, then H3O+, then OH, and all of those reactions are happening in water simultaneously. Describe the relationship between OH, the concentration of OH, and the concentration of H3O+ in an aqueous solution. The relationship is that the concentrations of both must be 1 times 10 to the negative 14th. In pure water, concentration of hydroxide and hydronium are 1 times 10 to the negative 7th, but in other solutions, you have to solve for it based on the pH. And the pH of any solution and the pOH, which is percentage hydrogen or parts hydrogen. Potential, oh, I was wrong. The potential of hydrogen and the potential of hydroxide. Yeah. Calculate pH from concentration of hydroxide and vice versa. Calculate pH from concentration of hydronium and concentrate pH from the concentration of hydroxide and vice versa. I can do both of those. Number 10, define a solution as acidic, basic, or neutral using the pH scale. I can do that. Anything below 7 is acidic. Anything above 7 is basic, and then the area like around 7 is neutral. And 7 is neutral. Calculate pH of a strong acid. Ooh, that one's easy. The pH of a strong acid is equal to the concentration of the hydronium. Jeez. The pH of a strong acid is the concentration of the acid, because it dissociates completely. I know what I'm saying in my head. I know. Oh my word. I know what it means. And I'm thinking it in my head. But when I say it out loud, I sound actually insane. Jeez. Okay. Like, the pH of a 0.1 molar solution of HCl, which is a strong acid, the concentration of hydronium is 0.1, because all of HCl becomes H plus and Cl minus, and H plus is hydronium. So that's what I was trying to say, is the pH is the negative logarithm of the concentration of hydronium, and the concentration of hydronium is the same as the concentration of the strong acid or base, because it dissociates completely. And then you can use the equation to solve for pH. Yes, that's what I meant. Number 13, define Bronsted-Lowry acids and bases, the proton donors and acceptors. Identify conjugate acid-base pairs. So the conjugate acid, like ammonia, when it reacts with water, and water is what's the term? Water is amphiprotic, which means that it can act as either an acid or a base. Gosh, I keep cutting my face off if I forget to slouch. So, goodness, I'm getting sleepy. So, the conjugate acid between ammonia, NH3, and H2O. The base is ammonia, the acid is water, and the products are NH4 plus and OH minus. And in this example, the conjugate acid is NH4 plus because initially ammonia is neutral and then it gains a proton and becomes acidic because it's a positive charge and it's willing to donate a proton now. And so its conjugate acid is NH4 plus. And then everyone knows that by now that OH is basic because it's the opposite to hydronium and whatever. So the conjugate base of H2O is OH minus because it loses a proton and now it's ready to accept one. Yes. Use molecular scenes to predict net direction of acid-base reactions. Use molecular scenes to predict net direction of acid-base reactions. What? Predict the direction acid-base reaction. How to use molecular scenes. The net direction. Frick. Does that just okay? So it's talking about. Chemistry Libre texts is one of my favorite things. It is very wordy though sometimes. Okay. I don't know what's going on. So, okay. So it's talking about. Oh wait, I remember this. So it means like in the chemical equation, which direction is it going? So you can use the acid, the molecular scenes. I think molecular scenes means this like situation that the molecules are in. Like you need to visualize what is actually going on at a molecular level. So the proton like moving. So the net direction of acid-base reactions is like how far to the right or left things lean. So like for a really strong acid, it would go to the right because it dissociates completely, but for a weaker acid, it'll lean more towards the left because then it won't dissociate completely. Okay, I get it. Define Lewis acids and bases, proton or electron pair acceptors and donators. Recognize a Lewis acid-base reaction. I think I can do that. It's like if electron pairs are being protonated or not, or electrophile nucleophile is Lewis because it's not just donating a hydrogen around. Yeah, and like any atom that isn't just a hydrogen has to be Lewis. assign oxidation states to elements and atomic states within compounds and within polyatomic ions. I can do that. I just have to remember that the electrons all go to the more electronegative atom. So like in HCl, it would be +1 and -2. Or no, wait. +1 and -1 because there's only one electron. Yeah, I can do that. 19. Identify substances undergoing oxidation and reduction. I can do that by assigning oxidation numbers and seeing which atoms are gaining or losing electrons. And 20. Identify oxidizing and reducing agents in a given reaction. Which, oh yeah. The oxidizing agent is the one that is attracting the electron that it loses, and the reducing agent is the one that is losing the electron because it's facilitating that. So the oxidizing agent, yes, the oxidizing agent, where is it in the textbook? Control F. Oxidize agent. Okay. So oxidation is the loss of electrons, but the oxidizing agent gains electrons. And the reduction is the gain of electrons, and the reducing agent loses electrons. Okay, so I was right. That's so irritating. Gosh, I better not screw that up, because it's so confusing. Okay, well, that is the last thing on the study guide. I think I'm in a good spot, and that only took me an hour. Wow, I was very focused. I think I'm in a good spot. Yeah. I think I did good. The test opens in 40 minutes, so I could take it in 40 minutes. Maybe I'll get some dinner. Ooh, I'll do the practice questions. Yeah, alright. I feel good. Well, thank you for going on this journey with me. Thank you for falling asleep, hopefully, to the sound of me struggling through chemistry. Hopefully that was relaxing. Hopefully that was fun. Yeah. Hope you enjoyed. Yeah, I guess that's really all I gotta say. Have a good night. Sleep well. I hope you turned off autoplay. I'm gonna start reminding people to turn off autoplay at the beginning of my videos, I think. Because it's important. Like, saying it at the end doesn't do anything. Probably already asleep. But I hope autoplay is turned off. I hope that you remember to set an alarm to stop playing. I hope that you get enough sleep. I hope that your day tomorrow is fantastic. I hope that you wake up at the top of your sleep schedule and you just feel great and rejuvenated. I hope the best for you. I'll see you another time. Hope you enjoyed.